Okay, for our problem, we have here an entrance to a toll bridge. 4 toll booths are open. Vehicles arrive at the bridge at an average rate of 1,200 vehicles per hour, and at the booth, drivers take an average of 10 seconds to pay their tolls. Both the arrival and departure rates can be assumed to be exponentially distributed. How would the average queue length, time in the system, and probability of waiting in a queue change if a fifth toll booth were open? So for this problem, we have to take note that we have to identify we have to convert actually our average arrival rate into minutes, since we are given with 1,200 vehicle per hour. So if we try to convert that one, our average arrival rate, that will be equivalent to 1,200 vehicle per hour all over 60, so that we can have here the equivalent value is 20 vehicle per minute. This is for our arrival rate. Now for our average departure rate, so it took an average of 10 seconds for the drivers to pay their tolls. So which means that the average departure rate will be 10 seconds. So if we're going to convert that one, that is 10 seconds per vehicle. So if we're going to convert that one, so that will be 60 all over 10, converting that one to minute. So we got here an equivalent value of 6 vehicle per minute. You have to take note that 10 seconds is per vehicle. So now, if we're going to have our traffic density, which is mu, that will be equivalent to, we simply have to add our uh, average arrival rate over our departure rate, which is equal to 20 all over 6. So this gives us 3.333. So we have now the equivalent value. So if we're going to have here, if we're going to have the ratio between our rho all over n, so which means that, so the ratio between our rho all over n is equal to 3.333. Our n, the number of channels, there are 4 toll booths, so divided by 4, so this gives us 0.833, and this is less than 1. So which means that since this is less than 1, so we're going to make use of our MNN queuing. So which means that if we're going to have that one, we're going to identify what would be the probability that there will be no vehicles in the system wherein there are 4 booths that is open. So probability that there is no vehicle in the system with 4 booths open is open. So we're going to make use of the formula, which is piece of O, and piece of O actually is equivalent, this formula is equivalent to, this is 1 all over summation of rho raised to n sub c. You have to take note that n sub c is the departure channel number. So this is all over n sub c factorial. So this is where n sub c is equal to 0, and n is from n is equal to 1, plus this will be rho raised to n all over n factorial multiplied to 1 minus rho all over n. So which means that if we're going to substitute that with this one, we have computed our rho, which is 0.33. So which means that if we're going to have this value, we simply have to get the summation. So channel number, there are 4, so which means that we're going to have, it start with rho raised to n sub c, which has 0, so that will be all over n factorial. So we get here, that will be equivalent to 1 plus So we're going to sum up, so which means that we started with n sub c is equal to 0. So rho raised to 0 is equal to 1 all over n sub c, which is 0 and factorial, so that is 1. So 1 over 1, so we get here 1 plus n rho 0.33 raised to 1 all over 1 factorial plus 333 raised to the second all over 2 factorial, then plus 333 to the third all over 3 factorial, then plus this will be 3333 raised to the fourth all over n is 4, then multiplied to 1 minus rho all over n. So rho all over n is 0.833. So 1 minus 0.8833 is equal to 0.1667. So if we try to simplify that one, you get a value of 0.0213. Now, what will be the average Q length? So that is denoted by bar Q. So if we're going to have the average Q length, actually the formula here is rho. A P sub O multiplied to rho n plus 1 all over n factorial, then multiplied to n. Then this will be 1 all over 1 minus rho all over n raised to the second. So which means that if we're going to substitute now, our P sub O is 0.0213, P rho raised to n plus 1, so of course that will be 3.33. So 4 plus 1 raised, that becomes 5 all over n 4 factorial multiplied to n, then multiplied to 1 all over the value to this, which is 0.1667 raised to the second. So if we try to simplify, we get a value of 3.287 vehicle. Now the average time spent in the system. So the average time spent in the system will be equivalent, that is actually bar t. So if we're going to have the value for bar t, that will be equivalent actually to, you will have here bar t is rho plus bar q all over lambda. So rho is 3.33 plus bar q is to 3.287 all over lambda, which is the average arrival rate 20. So we get a value of 0.331 minute per vehicle. Now if we try to get the value of having to wait in probability of having to wait in a queue, so which means that P of n is greater than n, so that will be equivalent actually. So the formula to this actually is P sub O multiplied to rho n raised to n plus 1 all over n factorial times n times 1 minus rho all over n. So which means that if we're going to identify the value for this, we have now the equivalent value, which is, if we try to simplify the values, which is 0.548. Now the second question is, what will be the probability of waiting in a queue change if a fifth toll booth were opened? So if the fifth toll booth were opened, so which means that we're going again to compute our P sub O, our average time spent, and the probability of having to wait in a queue. So we're going to compute all of those that we have done a while ago. So however, the only difference is that there are 5 booths open, so which means our n sub n here is actually equivalent to 5. So our n sub c, so we start with 0 to 5. So we make use again of the equations so that we can compute of P sub O, probability of having no vehicles in the system if there are if the fifth booth were open. So it gives us the result of 0.0318. You have to take note that, of course, we started from 1. Because we try to simplify rho raised to n sub c all over n sub c when n sub c is equal to 0. So simplifying that one, rho raised to 0 is equal to 1. So then let's try to substitute n sub c raised to 1 all over n sub c. So 1 factorial plus rho raised to n sub c. So that will be 2 all over 2 factorial plus rho raised to n sub c all over n sub c factorial. So that will be the third plus n sub c rho raised to n sub c all over n sub c factorial. Then plus this will be n sub c raised to the fifth all over n sub c. So 5 factorial times. So this one is 1 minus, this one is actually 1 minus rho all over n. So we have to take note that our rho is 3.33. So divide that to our n, which has 5. There are 5 booths that were open. So it gives us a result of, the value here is 0.66. So if we try to subtract this one to 1, so it gives us a value of 0.33. So you have here the result. So if we try to simplify, you get now a value of 0.0318. Now again, for the average queue length, so it will give us a value of 0.654 vehicles, and the average time spent in the system, it is equivalent to 0.199 minutes per vehicle. And the probability of having to wait in a queue is, this is p of n greater than n. So we simply have to substitute the values here, wherein our equivalent value for p sub o is 0.0318. The value for our rho is equivalent to 3.33 raised to n plus 1. So n is 5. So you have here 6 all over n factorial times 5 times n. So you have here 5 factorial times 5 times. This one is the result for 1 minus rho all over n. So we get a value of 0.333. So if we try to simplify the probability of having to wait in a queue, this is equivalent to 0.218. So therefore, if we try to open the fifth booth, it will reduce the average queue length by 2.633 vehicles. So that is actually substituting the value for the fourth booth. The average time spent, the average queue length, for, there are four toll booths that is open, subtracted to there are fifth toll booth that is open. So you have here 2.633 vehicles. So that is the reduction for the average queue length. Then the average time spent in the system, it will be reduced by 0.132. You simply have to subtract again the result from the 4 booths and the fifth booth, and the probability of waiting in the queue gives us 0.330. So again, the result for the probability of waiting, so from the fourth toll booth open and the fifth toll booth open, so you have a result of 0.330.